The subject of today's ECH 4123 class is vapor-liquid-liquid equilibrium. So in vapor-liquid-liquid equilibrium, you actually have three phases that can coexist together. So the main time this happens can occur if you would have vapor-liquid equilibrium, except the liquid phase contains a mixture of two things that are immiscible. Let me write that down. Yeah, so this occurs when you have, like I said, a mixture of two things that are in the liquid phase that would form two liquid phases, but you also have a high enough temperature for them to boil. So it's kind of a meeting of vapor-liquid equilibrium and of liquid-liquid equilibrium. So we know from experience that for vapor-liquid equilibrium curves, these are strongly affected by temperature. So for example, if I have a TXY plot for VLE, and I have an azeotrope that is occurring. So let's say this is what my TXY diagram looks like at a certain pressure. So this is for P is high. Now say I lowered that pressure, what would the TXY graph look like? It would probably look the same, just the magnitude would be different, right? So I would have, these are supposed to look the exact same, except my temperature is now lower. P is low. So the phase envelope, the bubble point and the dew point curves just shift vertically downwards if I decrease the pressure. What does the liquid-liquid equilibrium curve look like? No matter what the pressure is, it's going to look very similar. So it's, remember, liquid-liquid equilibrium is independent of pressure. Well, no, that's not right. It is less dependent on pressure, on P. And in most cases, if you were to plot two pressures on the same liquid-liquid equilibrium curve, they would kind of overlap, right? So this would be P high, and maybe let's do a different color, green, right over the top, but maybe just a little bit changed would be P low. Okay, so what's happening here is if I have a vapor-liquid equilibrium curve and I decrease the pressure enough, I'll also note that the temperature at which liquid-liquid equilibrium occurs is lower in general than vapor-liquid equilibrium. If I plot these on the same curve and I have vapor-liquid-liquid equilibrium occurring, so once again, I'm going to plot them all on the same TXY plot. So T on the y-axis, I'm just going to say composition because it's going to be vapor-liquid-liquid equilibrium. But then the subject of the first video, we'll just talk about the phase diagram and what those look like. So once again, if I have a TXY plot, this will be for a high pressure. As I keep decreasing the pressure, this envelope is going to move downwards. I've got the liquid-liquid curve like so. All right, so these are for P high and P high. But now, if I decrease the pressure, remember, the liquid-liquid curve is going to approximately stay where it is. The TXY curve, the vapor-liquid curve is going to keep going downwards. So what happens when they intersect is when we get vapor-liquid equilibrium. Vapor-liquid-liquid equilibrium occurring. So I'm going to draw a large plot that's detailed. So this is what the resulting phase diagram would look like. So notice it's just like the TXY, I'm sorry, I keep saying the TXY, they're both TXY curves technically. The vapor-liquid equilibrium curve is coming downward, and at the point where it meets with the liquid-liquid equilibrium curve, it's almost like the liquid-liquid curve gets its top chopped off. And this is what the resulting phase diagram would look like. So there's a couple of lines here. I'm going to talk about all the regions of the plot. So in the uppermost region, so I'm going to write in gold here, this region up here would be one vapor phase. All right, so if my overall mixture composition coordinate and my temperature coordinate are in this region, I just have one vapor phase. The overall mixture composition is the composition of the one vapor phase. All right, in this region, I have vapor-liquid equilibrium only. So I'm just drawing one example point, by the way. I'm not, it applies to the entire region. Vapor-liquid equilibrium is there, where I draw a tie line, which would give me the composition of the liquid phase over on here. So this is the composition of liquid phase, of the one liquid phase that exists. This is the composition of the one vapor phase that exists. Same thing for this part of the curve. So this is vapor liquid, where if my coordinate is there, for example, I draw a tie line. This is the composition of my one liquid phase. This is the composition of my one vapor phase. Down in this region, I have liquid-liquid equilibrium, where, just like I was talking about last time, we draw a tie line like this. I have two liquid phases. The composition of one liquid phase is there. The composition of the other liquid phase is there. Moving along on my flanks, these regions on the outside of the graph are where I have one liquid phase that exists. And if I have one liquid phase, then I don't have different compositions. I don't have to draw a tie line. Same thing out here, I have one liquid phase. And that covers all the regions of the plot. There's one more area of the plot that's potentially very interesting. Notice I haven't talked about where vapor-liquid equilibrium occurs. That is if my temperature is on this line. This is supposed to be a straight line, by the way. Most of the time it's straight. I just drew it kind of curved, I guess. Or I drew it where, you know, the liquid-liquid curve is supposed to intersect with the vapor-liquid curve such that this line is straight. So if I have a composition anywhere on this line and the temperature is at this specific temperature, which does change as a function of pressure, remember, because pressure is going to change how far this vapor-liquid curve is shifted up or down. All right, so say I have a composition that is there. So this is X overall, and my T is there. How many phases do I have? This is where I have vapor-liquid equilibrium. So I have two liquid phases. The composition of the liquid phases are given by these 2 points. So this is liquid phase 1. That's the composition. This is liquid phase 2. And I have a vapor phase that is at the azeotrope. This is called a heterogeneous azeotrope. Vapor phase composition for vapor-liquid equilibrium. All right, so quick first video today. In the second video, I'll talk about modeling approaches, and then in the third video, we'll do a practice problem.